Around November of 2020, I decided I wanted to build an Antweight combat robot. These machines weigh 150 grams and fight for 3 minutes in an enclosed arena. Having kept up with the televised robot wars and BattleBots competitions for most of my childhood, I had a rough idea of what made a good robot. Ringspinners seemed very attractive for their potential for heavy hits and 360-degree weapon coverage, so I started designing my own. This video documents my development process and lessons learnt going from my first robot, which didn't even spin, to the latest iteration which uses a unique custom Hubmotor technology. Ringspinners are a fairly rare breed of combat robot due to the difficulty of making them work reliably in a combat setting. For a ring to work, it needs to stay round, it needs to be accurately constrained radially and axially. Often this result is a complex, many-component machine. This is easy when forces are predictable, but forces on a robot in this sport are anything but predictable. With the added disadvantage that more parts generally means less weight for structural strength and more things to go wrong. Being vaguely aware of this, the first design was meant to be as simple as I reckoned I could make it. At my disposal was a simple CNC router, a 6040, and a manual lathe. Mark I had a two-piece HDPE plate chassis, 4 machined steel rollers, and a composite ring of HDPE, aluminium and steel, fastened with metric 2 bolts. I had many wild designs for a laser cut gear drive, a sawtooth disc, a launcher disc, and massive hammer rings, but practically started with the traditional single tooth impactor, friction driven from a small drone motor, 1306. Batteries, ESCs and motors were picked based on whatever Hobby King had at the time. With all parts machined, bar the mild steel impactor, which I got water jet cut, it was time to see if version 1 worked. After immediately blowing up my first ESC, I tried to spin the ring in the vise, but no dice. The small motor did not have the torque to overcome the friction in the system, even with a starting push. I hope to attend an event in Melbourne coming up soon, so rushed to fix the design. I reckon the main cause for excess friction was the rollers. They were turned from some very rusty rebar I had found, and not turned very skillfully either, with significant dimensional deviations, had a bit of a taper, the diameter wasn't very accurate, and the thicknesses of the flanges were all over the place. So something had to be done. Mark II used 16 miniature ball bearings to constrain the ring, 8 on 4 posts for radial constraint, and another 8 on individual fasteners for axial retainment top and bottom. For such a complex part, the chassis was 3D printed, quite an unknown technique to me at the time. The printer reasonably handled the tolerances for mounting the bearings, and the bearings themselves spun freely, unlike the rust-pitted rollers I had before. The 6 amp ESC was upgraded to a 20 amp one for good measure. Otherwise, using the same components as the previous version, it was time for a test. While not the safest way to validate the mechanism, it showed enough promise to push ahead with the concept. The rest of the control electronics were assembled, including the then new version 1 Malenki Nano, and it was on to full robot testing. The first major improvement was to use small brass washers to space the radial bearings off of the chassis. This led to a much more reliable starting from the low torque motor. Then it was using heaps of Loctite to keep the radial nuts from backing off when the screws turn, as some of the torque was transmitted to the screws from the ring, even though the bearings are pretty low friction. TPU drive wheels were tried, but in the end O-ring tyres were used. At this point it was ready and reliable for competition when,
with both the Victorian Premier and the Prime Minister of Australia, Mr Morrison, that New South Wales and Victoria will be shutting down their borders.
Eventually the robot made its way to the first event in Melbourne alongside a couple of others I had built in I think about a year it had been since I first started this project. We made our way up to Melbourne. The Ringspinner did pretty well. It split some chassis, it avoided falling into the pit, and eventually went 3-0 to win its first and my ever first outing as a destructive Antweight.
Other side of it, if that makes sense.
Overall quite the success, but in one match the O-ring that was epoxied to the motor came off. This was very quickly repaired at the time, but was a sign of things to come. A few months later, I took Revolve to probably the largest ant and beetle event in the country, known as ARC Robot Havoc in Adelaide. There the ring did pretty well, now upgraded with fancy polyurethane tyres, and a ring that I'd machined myself on my new mill, but revealed the significant drawbacks of the current design. A few times the O-ring detached from the motor belt, which caused a loss of the weapon. When it got a good hit, significant damage was done, but Revolve tended to lose weapon-on-weapon impacts due to the comparatively low tip speed of the Ringspinner, because the weapon was effectively geared 4-to-1 off of that friction drive, which is a significant loss of speed versus other weapons which were typically directly mounted to similar style and therefore similar speed motors. There's also a significant loss of stored energy because of this. Even though the ring was very large and very heavy for an air weapon at the time, if all else was equal, spinning at a quarter the speed meant 1/16th of the stored energy. As seen in this clip, despite breaking the opponent's weapon mount, my robot was almost launched out of the arena by Segmentum's weapon catching the underside of mine before I hit theirs. This hit also bent the ring pretty badly. The Ringspinner didn't make the finals by 1 point, so I had some fun in the rumble, and then was put to the side for other shenanigans.
Spiderbot is a pneumatic powered spider with its own built-in compressor.
Get him while he's down. Oh, he's smothering him!
Overall, this robot had some good design elements. The HDPE ring runners worked very well. Integrated Blanky Nano controller proved reliable for a new part on the market. The 3D printed chassis proved worthwhile, and seemed to prove that Ringspinners do have a place in Australian ant combat. But there were definitely a few things to improve. The next Ringspinner had to address a few issues. The machine needed higher weapon RPMs to match the field of direct drive spinners. It needed a much more durable ring. The thin mild steel was always going to bend. The HDP and aluminium sandwich didn't actually add to the strength much. It was only there to space the ring for the rollers to run on them easily. Ideally, the robot will be thinner next time to increase the stability. A better way of driving the ring than friction drive was needed to be more efficient, need to be more reliable. Better epoxy might have helped the O-ring coming off, but it wouldn't save the fact that the friction drive was very inefficient and the O-ring itself would wear and no longer contact the ring if it spun loose. And also generally I learned a lot since I'd started making that robot, so it was time for a brand new one with the new skills and techniques I'd learned. A few initial concepts for Mark III were drawn up, including this ultra thin one, with very similar concepts, but eventually I arrived on a new concept that should solve all the aforementioned problems. I will use a custom, unique, brushless Hubmotor with the robot built inside of it. If you squint real hard, a Ringspinner kind of looks like an outrunner motor. Brushless outrunners are the ones typically found in drones, where the stator coils sit inside a motor bell which contains the magnets. Revolve 2 used one of these outrunner motors to drive the ring, but my idea was that the entire robot could be built like an outrunner, or a Hubmotor in this case because it was direct drive, and this will give efficient and reliable running. So the theoretical advantages are a very efficient drive, with the only friction coming from the bearings or whatever would constrain the ring. This will improve spin-up time, top speed, battery life. It'd also give a great increase in power. The motor would be genuinely huge for an Antweight. The stator volume, which is the literal space that the stator coils take up, would be more than entire weapon motors that other robots would use. The rotor magnets would add to the weapon mass in a moment of inertia efficient way, which means the weight is being used effectively. And finally, the ring could hit higher speeds with a custom wound motor, as I could choose my own specifications outside of what was typically available on the drone market. The real crux from this is that, from my understanding, a BLDC motor doesn't need all of the stator coils. Theoretically, just one set of 3 full 3 phases was the minimum requirement to make it run. Potentially that left enough room for the robot bits and enough weight, as I didn't need all of that steel that would be in a full motor. The only problem was that I didn't know how to build a motor. Looking into BLDC motors gave seemingly 2 options, star or Y wound, and a delta wind. Delta seemed to have more RPM when everything else is equal, so I started with that. Stators could be found pretty cheap from China, so the robot was based on a 110 stator iron. Going one size down didn't leave enough room for the robot bits, so that was the limiting factor. The basic shape of the robot was set. Based on the tried and true method of gut feeling, 6 coils will be used out of the original 36 for 2 sets of 3 phase pairs. Due to the lack of a steel backing, which helps direct the magnetic field of the rotor inward, extra magnets were placed in a Hubmotor array at the suggestion of another builder. These extra magnets directed the field for increased power allegedly, but importantly actually caused the ring to have magnet redundancy. In the case of one magnet being lost, the ones on either side of it would keep the field intact if at a lower strength, should allow the ring to keep running. When modelling the robot, it was hard to get it looking right. 2 wheels, tried 4 wheels, it didn't look good at all. But filling those cavities with a visually complex walking mechanism looked about right. In the rule set that most events in Australia follow, a cam walking robot is allowed a 50% weight bonus. So not only would this solve my aesthetic problems, but would also grant me an extra 75 grams to work with, which pretty much became essential later on down the track. To thin the robot, I ditched the wraparound bearings and settled on flanged ones to constrain the ring. This lowered the profile and reduced the number of parts, saved a bit of weight. Secondly, the ring was made out of a pair of aluminium parts that increased the bending stiffness over the thin mild steel in the past. Titanium teeth would be used to reduce the wear versus mild steel, all sandwiching an ABS printed magnet retainer to space the magnets correctly. Finally, the end product would use a carbon fibre chassis to make it very lightweight and very rigid. The plan was set. Mark III would be a 225 gram shuffling sector stator Hubmotor Ringspinner, quite unlike anything that had come before it. Step 1 was to prove that I could make a shuffling mechanism work at all. There are a multitude of ways to go about this problem. I'd settled on a 3-foot dual cam system for minimising complexity and size while retaining invertibility, which is pretty important. It's not the best walking mechanism, but should work for our purposes. Parts were printed, and soon enough a working prototype was made after many, many prototypes. Tolerances on the cams proved to be the biggest challenge, so they were clocked at 120 degrees using length of paperclip, and the feet had very loose holes to allow for some wiggle room. Relatively high power 3 volt, 1000 RPM and 20 motors will be used to drive these mechanisms. With this proven, parts were machined on my mill, thinning out the stator and making aluminium rings out of 7075 alloy. Enamelled wire was hand wound around the coils, about 16 turns per coil. N35 neodymium magnets were glued into the ABS retainer in the Hubmotor array. A compass was used to determine their polarity. The sandwich was then glued together with araldite epoxy, all assembled into a printed chassis just to test to prove the concept. Despite running very freely, the ring didn't want to start up at all. A lot of twitching, but never spun a 4 rotation. Eventually, I realised that the magnet to coil ratio, which I'd selected, just didn't work with a delta wind. Turns out, different winds need to match some ratio of stator to rotor poles, and my ring was constructed for a Y wind with a 36S48P construction. After rewinding, more tests failed due to improper insulation between the coils and the stator iron. Eventually, after many more small problems were fixed, the first spin-up finally worked. Not good enough for combat, but proof enough of life to push forward. Impactors were machined by sacrificing a few end mills to the titanium gods, and the robot assembled into a could-fight state. Further testing found that once spinning, the motor could idle at very, very low RPMs. Therefore, the problem of the starting sequence was definitely in the starting sequence. When the electronic speed controller transitions from open loop control, where it just on a clock cycles between the coils to get the motor started, to closed loop control, where it uses the back EMF of the magnets going past the coil to sense where it is, that transition wasn't happening, so something was happening there. After hitting a few test chassis in a safe environment, it was clear the ABS frame was not up to the task and would flex, permitting the ring to just pop off its rollers. Carbon fibre parts were milled and implemented, which solved the problem. Switching to a 30 amp ESC helped the starting sequence problems, and the machine was ready to fight with a new electronics package. The concept ticked all the boxes set out for this design, but rarely does a plan hold up in the arena. Ready to fight, Revolve Mark III went for its first match at the inaugural Wollongong event, up against a hard-hitting vertical spinner named Parasite. The first hit immediately dislodged a magnet and jammed the ring, and when the vert came in for a second hit, it split and bent the aluminium rings completely, which ended Revolve's first outing due to being basically irreparable at this point, with what it had available at the event. Improvements were made by epoxying all the magnets instead of just supergluing them, machining new aluminium rings that had a large flange to increase the bending stiffness further on the individual parts, not just the overall ring. Think of it kind of like a piece of extrusion versus a flat bar in bending. This also gave more surface area for the epoxy to bond, which should increase the ring strength overall anyway. With a new chassis and hardened steel impactor teeth, it was totally fine to see if the concept improved viability. The first fight it saw was up against a horizontal spinner named Pancake. Revolve removed one of its wheels early on and ended the match by pushing it into the pit, but lost the ring mid-match. This failure was caused by Pancake punching a hole in the aluminium ring which dislodged a magnet. That was okay due to the redundancy, but a bigger problem was caused in that the ring had warped and had become oval. It wouldn't spin anymore. There was a vice to help me straighten it out. This happened in the next fight too. Revolve also won that, did some good damage, but again a warped ring. The third fight, another vertical spinner named Uppercut. Once again, removed the wheel and eventually pitted them, with more warping. At this point, Revolve was in the finals, but had to withdraw as the ring was becoming square-shaped because of the way the vice could squish it. It was no longer circular, you just couldn't fix it. So partial success, but it was very clear that more work had to be done. So here's where we can talk a little bit about metallurgy. So one of the big changes, it ended up being a big change, but at the time I thought it was a very innocuous change. We're shifting from 70-75 alloy to 60-61 alloy. At the time, it didn't seem like such a big deal, but the 60-61 is significantly less stiff and has half the tensile strength of 70-75. Remachining the rings to be thicker, made of 70-75. The third variant was bonded with a long cure epoxy over the 5-minute stuff I was using previously. At this point, the ring weighed 100 grams, which is by far the heaviest ant weapon in the country. At this point, I'd run out of weight in the 225 gram budget as well. So if there was any changes, I was going to have to try and find it somewhere, so I really had to hope this version held up to competition. Third event for Mark III was another of the local Wollongong ones. Its first and only fight was against Pancake, though much improved. The first hit dislodged the stator, and further cuts from the undercutter broke the shuffle pods. Without spares, Revolve was out for this event. Got a chance for some payback with one of my other robots later on though. Therefore, the true test of Revolve Mark III would come at the next Adelaide Robot Havoc event, 1 year after Mark II fought there. This time round, though, things went quite a bit better.
One, fight! rank tail, but it's mixed. Oh! Massive hit! Oh, and again! William rank tail flying all over the place for a ball. A little bit unstable right now. Can William rank tail take advantage? Hits open.
Oh!
Are we going to see a similar fate that we saw from high voltage earlier? William Ragtail gets some good hits in.
Oh!
Just avoided the pace. Compose yourself, William Ragtail. Oh, over it goes again. Oh! Massive hit again.
No, 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 no!
That pace.
Oh!
How many more are we going to see more dodges like this?
Oh!
Yeah, one from behind Jesus is just skipping across the edge of the pit like that. This is fast and furious action right here. Revolt, unsteady. Oh, good hit on high voltage.
Get it steady.
Revolt's in trouble.
Oh!
Not quite the right bounce.
Oh, oh, oh!
Steady.
Yeah!
Is it too late though?
Oh!
How much time?
15 seconds off.
Oh, Revolver stopped again. Oh no.
10,
9, 8, 7, 6, 5. One more hit.
3, 2, 1.
That's it.
Cut it.
The new ARC Ant Arena was like driving on ice, which meant the inner robot would spin before the outer ring because the ring had a higher moment of inertia than the entire inner chassis of the robot. Despite this, Revolve got many good fights and did real damage. Went 3-1 in qualifiers with one loss for falling in the pit and no real damage. Revolve then won its quarterfinal against a good horizontal spinner by a signature de-wheeling. The semi-final was with another neat shuffling ring that used a friction drive with a 4S power system and also a TPU chassis vertical spinner. This latest failure mode popped up. The ring had been slowly expanding or creeping due to centrifugal force, causing it to pop off its rollers in the fight. Overall, quite a success with a 4-2 record. And with that, we're up to date. It's been quite the development journey to get here, and there's still more to come. Overall, Mark III achieved its design goals set out after Mark II, and the custom motor could lead to more unique designs in the future. This current challenge will be to solve the creep issues, or at least mitigate them. Unlike steel, aluminium has no fatigue limit and will slowly stretch until failure. The best way to deal with this will be with adjustable chassis rollers, so that I can just adjust the ring tension as it stretches, but it means that the ring has a fixed lifespan and eventually will be just too big. And each ring takes about 8 to 10 hours of good labour to make all the bits and glue it all together. So preferably I wouldn't be sacrificing the ring if I can avoid it. I'm happy with my contribution to the Ringspinner lineage. Despite their limitations, the sheer maximisation of energy storage and deliverance has and continues to have a place in modern combat robots. Thanks for watching this development catalogue. I've got a few more outstanding robot projects and they'll be made into videos in time. If you're interested in combat robots in Australia, it might be a club near you, with most of them active on Facebook. Until next time.